So welcome everybody. Hello. This is introducing EntityGraph, Ergonomic Data Store for Application State. That's my name, and that is my email address. Feel free to reach out for any reason if you want to chat. And so what this is a Clojure library and a Clojure script library. And it is in this space of client state, application state. It was targeted at single page applications, but you can use it for other things as well, obviously. And it's an immutable data store. I wouldn't go as far as to call it a database, but it's kind of database-like, right? It's all in memory. And yeah, it's for your application state. And it's based on the triple store concept, entity, attribute, value. So this is all heavily inspired by the Atomic and data script and that data representation, that data model. There's also a T there, grayed out, because we don't really keep a T, and we'll see more details on that later. And there are basically two indices, the EAV index that contains all of the entities, and the AV index for select attributes as needed. And the indices are Clojure maps. And that's kind of like one of the key things. And for reading data, it supports pull style queries. So again, if you're familiar with the Atomic data script, you know what pull looks like, but these are graph queries essentially. And there's no declarative way to query the data. There's no data log or SQL or anything like that, because 90+% of the time you'll be using pull. And then when you need something that's beyond pull's ability, you just hand code a function and you leverage the indices because they're exposed to you to just pull the data that you need, to query the data that you need. And here we're trading like the declarative nice queries for hopefully some performance and a smaller footprint. That's the idea. So these are just some features really quick, all very familiar to you if you know the Atomic. Temp IDs, keyword entity IDs give you nice programmatic names. That's something that's not in the Atomic data script. You have attributes that can be cardinality one or many. And for cardinality many attributes, a unique feature is that you can store them within an entity where you can store them in a sorted order. You have reference attributes and component entities. Unique identities values are also supported. Lookup refs are supported. Nested entities and assertions. So if you have a nested map or any number of nested maps, any number of levels, if they're coming from reference attributes, they will be interpreted as separate entities for you, and you can just transact and everything just works. There's an AV index sorted by a custom comparator if you need a custom comparator, and pull queries. So these are non-goals. These are problems that this library does not solve, does not intend to solve. Synchronizing data between client and server, that is always like an issue. How do I handle that? And I did consider maybe providing a solution that works together, but I thought that would make for a rather brittle approach. And I thought instead it would be better to have a flexible client DB, like on the client side, that can support varied backend approaches, right? And just allows for experimentation. So we're not concerned with syncing data in any particular way. Storage is also not really something I thought about too much. It is possible, if all your data is serializable, it is possible, of course, to just write it to disk. But I haven't found that to be particularly useful. Also, like IndexedDB in the browser is not great. So the focus is really on like your client state in memory, not like storage and persistence to disk. And reactive queries are also kind of something kind of cool and interesting, and maybe even offer some performance benefits potentially, but I did not worry about it too much. I did sort of consider it, and I found it just faster to, like, if you're using something like Reframe, to just requery the data, and it's just as fast as trying to do reactive queries. But if you want to try, it's possible to build on top of this, and we'll see later how. Or if you want to react to the changes that are happening in the database for other reasons other than querying, you can also do that. So why did I venture into this space? I mean, there's already solutions, of course. Well, I guess the main answers because I just wanted to. I just felt like it. It kind of became like a rabbit hole, one of those issues. But still, I have some reasons that I justify it to myself with. So let's take a step back. So we're talking about single page applications, something like React, or there's other libraries, of course. And in the Clojure script world, we're talking about primarily Reframe. Again, there are other libraries, frameworks, if you want to call them that. And there's basically two ways to keep state of your application, two sort of philosophies, right? One is like a fragmented local state. So you have your component, like your React component, some UI element, and the state for that element lives with that element. So if you use like React's use state hook, that keeps the state right there in the element, and you up in the component, and you update it there as well. And so your state is distributed all over, your application that way. And some people do prefer to do it that way. I do not. I lean far more towards the centralized global state model that, for example, Reframe uses, and something like Redux and this other stuff also in the JavaScript world. So it's primarily all the data is stored in one global data store. Of course, if there's like some transient form state, you might not want to do that, but most of your application state would be in a global state. So we're playing in the space of, we have global state. How do we deal with it? How do we organize it all? And so the first kind of obvious solution is to just use a Clojure map, and it's a good approach. People have built very complex things just using a Clojure map, but it does have some limits. So, for example, a map is a key value pair, right? So that's the structure to your data, and then if you nest them, you get this hierarchy, and you're always thinking about, how do I organize things, right? Like, which key do I put this under? What path should this live under? Because I have this query here, I have this other query, and they kind of need the same data, and there's some overlap. And if I store it like this, then it'll be easy to do this query, but this query is a little clunky. If I do it this other way, should I maybe do it redundantly, but then I have to keep it all in sync? So these are things you're dealing with kind of ad hoc. And always you want to link your entities together somehow, right? You want this thing to point to that thing. And so that's a reference, right? That's what like in Datamic or DataScript would be a reference attribute. And again, you're sort of implementing this ad hoc, what your references look like. But again, this is all doable, but I thought maybe let's not do it ad hoc. Let's try do it a different way. It would be nice if the thing, our global data store in our application kind of looked something like a database, had a certain type of information model to it. And so I played around with DataScript, and I liked it. And it felt a bit less ergonomic maybe than I would like it to, but you can be the judge of that. And there's some minor things about it that sort of accumulated for me to where it didn't feel quite like what I wanted to use, although again, I really like DataScript. Like, it keeps a transaction ID for each datum, but it doesn't keep history by default, so the transaction ID kind of doesn't play much of a role there. Compared to DataScript, EntityGraph has fewer indices, no AAVT index, and just a limited AV index for just what you choose to put in there, in addition to a couple of other things that we'll see. And one thing that was an issue was data log queries in DataScript were actually a little slow. And maybe it's been fixed, I don't know, but I think there's just an inherent problem. You have to parse the query, and then you have to run the query engine. And what I ended up doing, and actually the author of DataScript, Nikita Prokopov, has written about this, you just end up scanning the indices directly for performance reasons. And the indices, they have datums in DataScript, they're BT sets, and you just scan them directly, and that's how you query your data, aside from pool, of course. And so I thought, if we're going to go to the indices like that, like, wouldn't it be nice if they were maybe Clojure data structure? What would that look like? What would that enable? How would that sort of feel to program with? Okay, so let's take a step back. I've been referencing Datamic and DataScript, and maybe some of you don't know what this is. So let's just kind of cover a couple of the basics, just so we're all on the same page. What's an entity? What's an entity ID? So an entity is just a map of attribute value pairs. It's an open map. You can put any attributes in there. But there's a special DBID key that signifies the entity ID for that entity. And that's your internal database key, basically, like a primary key. And entities are indexed in the EAV index by this DBID key. And then for some attributes that you define, that you need to later maybe query, we also place them in the AV index, which is also a Clojure map. And so this is just what an entity looks like, that first map. And then entity IDs are auto-assigned integers or user-specified keywords. So that, I mean, programmer-specified keywords, you're the user of the library. And here we have an example. We have a DBID of UI chat window. So that if you want that particular entity, you don't have to reference it by some integer that's kind of meaningless. Sometimes you want that. It's really nice to have. And so you can refer to it by its keyword, entity ID, UI chat window. You can, do things with it. And then we have attributes. They're just keyword keys in entities. They're sort of analogous to columns in a SQL database. And then if the attributes are like columns, then entities are like rows, but these rows have no predefined, column sets, right? They're just open, and any attribute that's available, in the database, you can have it in your entity or not have it in your entity. And some properties must be specified in the schema. So if you want the attribute to be cardinality many, you have to specify it. If you want it to be a reference, you have to specify it, but otherwise you don't have to specify anything. And just for cardinality many attributes, we represent them as a set, and we'll touch on that later. But here, person nicknames, you see a set there, and has two values. One is Johnny, the other is Versace. So that's what a cardinality many attribute looks like. And now for values, they can be any data type, including, collections, including anything, absolutely anything. And you don't have to declare what the data type is. And again, this is just like data script. And attribute value types are heterogeneous within and between entities. So basically anything goes, you can have a cardinality many attribute that all the values are of different data types, right? So anything you want. With one exception, if you want a reference attribute, if you want an attribute that points to another entity in the database, then you got to let me know. You got to specify that in the schema, and that'll create a graph for us, and then we can use pull to, do our query. And nil values are illegal, so if you have something that's nil, just don't have that attribute. All right, so the overview of how you use EntityGraph is create a schema. It's attribute level schema. You create a database with that schema, which returns to you a database value as a Clojure map, and we'll see what that looks like in a second. Then we write some data. We add, remove, update entities, and we use transact for that. And then we read data declaratively with pull primarily. And then if we need something beyond that, we can read from indices directly. So that's just the overall picture. Now we're going to get into the details. But before we do, let me just mention, as far as keeping time and history, EntityGraph does not keep a history. There's no transaction log, no timestamps recorded. But your successive database values are just immutable Clojure maps. So if you need a past value, you just hold on to a reference, and you can have a past value. And of course, we don't want to accumulate all of them because we're in memory here. But if you need one, you can have one or several. So for example, maybe you do something speculative, some speculative update, but you keep a version to the previous, you keep a reference to the previous version, and then you do the update. You make sure like it checks out, everything checks out, and then you can let go of your reference to the past value. Or if something went wrong, you just revert back to that past value that you held on to. And the only thing that we have as far as related to history is a dbtx count for the overall database. It just increments every time there's a transaction. So we won't have too much code here, just a few slides of code, just to give you a sense of what things look like. So here we create a database, an empty database, and so we call createDB, and we supply it with a schema with just one attribute in the schema. And we're going to say, well, the attribute is first and last name, and we're going to say, I want this in the AV index, so that's why we have DB index there. And I want that index as a hash map, and we'll see what all that means. And then down below the arrow, it returns us this. That's our database. This is the database value. So we can examine the keys here. So the first is DB schema. That's just for internal use. It's exposed to you, but you don't need to worry about it. There are helper functions when you need them to help you make sense of this, but you don't need to worry about it. It's just there for internal use. Next ID, that's also for internal use. That's just keeping track of the next entity ID that'll be assigned when you transact new entities. TX count 0, that just gets incremented every time there's a transaction. And then at the bottom, we have the two indices, the EAV index and the AV index. And right now they're empty, but in the AV index, we can see there's already room for indexing that person last name attribute. So now we get to transactions. Again, if you're familiar with the Atomic data script, this is all very, very familiar. And but just in case, we can have these operations, db add for asserting data into the database or making updates, retractions do the opposite, they remove data, and then retract entity, that just retracts the entity, all of its components, and we'll talk briefly about what that is, and all references to the entity and to the components, just like a erase from the face of the earth. And transaction data, again, just like the Atomic data script, can be in list form or map form. Map form is for assertions only. And as mentioned earlier, nested maps are supported. So if you have some under a DB reference value type attribute, if you have some other map there, it'll be interpreted as a separate entity. And that's just really convenient when you're bringing data in and transacting it. Temporary IDs are supported, and again, temporary IDs, they help you assert new entities, or you can also just omit the DB ID key entirely. But with temporary IDs, it's a string in the entity ID position, and it then, after transaction completes, it gets resolved to an actual entity ID. And all instances of a temp ID map to the same entity ID. And also upsert is supported. So if you have a DB unique identity attribute, if you define some attribute to be a unique identity, and then that's found in the current value of the database, the temp IDs that map to that will all sort of upsert into that entity. And having a DB unique identity attribute is very convenient when you're working on the client side, because you want to have some kind of a mapping between what's on the client and what's on your backend and system or systems. And so typically that's some kind of an external key. It may be just a primary key or a username or something. It's whatever you want. And that's where having a DB unique identity is really handy. So just a bit more code, just to, again, get a feel for it. We don't have to read all through this. But right at the top there, we're going to transact into our empty database. And we're going to have a transaction data. The first thing is a map. This is Jim Morrison, first name, last name. And then we have Nina Simone, sort of expressed as two vectors that have in the second position the string Nina, which is your temp ID. And then we have the other attributes there. First name Nina, last name Simone. And when we transact, we get a TX result, right? And so we examine this TX result below, we see what it looks like. DB before, DB after, those two keys I think are self-explanatory. And then at the bottom, we have temp IDs. So we see Nina gets mapped to entity ID 1, and TX data, that is the transaction data, but massaged a little bit differently. So this is a point of departure from Datomic and DataScript. We don't see actual individual datums here because we don't really work with datums directly or store datums directly in EntityGraph, but it's just a representation of what you've transacted in that transaction. And it's mainly used for debugging, but you can also, when we were talking about reactive queries, on each transaction, you can read this and react to it in some way that you find useful. And after we've transacted now, let's look at what the indices look like. So we see on the bottom there, we do a select keys on the DB after, and we select DB EAV and DB AVE. Those are our two indices. And highlighted in yellow is then what we get. That's what the indices end up looking like after we've done this transaction. So we have in the EAV index, we have two entities that you see there, Nina Simone, Jim Morrison, and then we see the person last name. We see that attribute has already been indexed. Transact took care of that. So we see that the last name Morrison is held by entity ID 2. And so there's a set there with just one entity ID in it. And Simone is that value is with entity ID of 1. So here I've copied the highlighted bit just for reference here because we're going to talk about indices. So EAV index, I think it's pretty clear what it is by now. Contains all the entities. And then AVE, for the AV index, let's discuss that in a bit more detail. That's attribute value entity. And that's how the map goes, right? Attribute value entity. And all the reference attributes get automatically indexed in the AV index. So if some attribute you declare in your schema is a reference, we'll automatically index it in the AV index. And we need it because we can navigate our references in reverse as well. We can go backwards. And to do that quickly, we need to have that AV index. And unique attributes also get automatically placed in the AV index because we need to be able to perform fast uniqueness checks when we transact. Aside from that, the programmer can specify what to index. So we don't want to index everything because maybe we don't need it, right? So we specify, and only those things we specify will get, will allocate memory in the AV index for those things. And that, of course, lets us retrieve data quickly for certain types of queries at the expense of the additional memory space. And as you can see, the AV index is non-covering, meaning we don't place the whole entity in the E position. We just place the entity ID, and then if we need to get the entire entity, we extract it from the EAV index. And so this is how this goes. Transactions update indices, produce new immutable database values, new things that look like this. So I want to contrast this now with another way that people have approached this. So this example is from Fulcro, but there are other solutions that take this approach. You can call it the typed map approach. So basically, you have nodes that are stored in quote-unquote tables versus in EntityGraph, just a single EAV index, right? So here we have person and address, quote-unquote tables. And then we have edges represented as vectors of table and ID. So you can see their person address 42. That's referring to another table right below it and a particular entry in that table. And so just one small thing to note here is that we're allocating a vector for each reference here versus in EntityGraph, it's either an integer or a keyword, which is more efficient, but maybe it's not such a big deal. What this enables you to do is this approach is, if you want all of some type of entity, if you want all the users, all the persons, all the addresses, all the products, like in that table that you have, you just get, products or users or whatever, and you can quickly get the whole list. But in how would we do it in EntityGraph? So we would have to rely on the AV index, and we have to check for a presence of some attribute that defines that entity type. So for example, let's say we want all the users. We would, and let's say all users have a user ID. So we'd index that attribute. Maybe it'll be a DB unique identity, so it'll be indexed automatically. And we'd say, well, let's see in the AV index, okay, these are all the entities that have that attribute. And then we'd pull them out from the EAV index. That's how we do that. And sometimes there isn't an attribute, rarely, but it happens. There isn't any one attribute that we can use for this purpose. So we might include like a type attribute just, to do this, but this is not common. So it's slower. This is obviously slower, but it's still fast enough. It's still quite fast. And if the number of items is small, like 10 or 100, I mean, it's fast. If it's 1,000, it's still fast, but then you're not even unlikely that you'll dump all 1,000 rows like on the screen, right? In your user interface, you're probably going to select some subset. Maybe you're going to paginate, and so maybe you'll sort them in some way. And for that, you're going to be needing the AV index anyway, or something, unless you want to scan your whole, the whole table. And so I felt that the EAV index, just having one index, like no like type maps, no like tables, quote unquote, I felt it was a bit more flexible. It just kind of felt nicer to me, especially having used Datomic before. So I went with that. Also, if you want to navigate your references backwards, you need something in addition to this, right? So if you want to say like who has the address 42, unless you want to scan everything, you need something in addition to this, some kind of an index. And while we're sort of on the topic, this is what it looks like, just to give you a sense. This is what it looks like to scan datums in DataScript when you're doing certain types of queries. And as you can see, like just to cover the first example, EAVT, so you specify which index you want to scan, and then you put some restrictions there, right? So, and then you get all the datums that match that. And of course, you can turn this into a map. You can just massage this into a map, but wouldn't it be nice if our index already contained maps and we can just pull out those maps? I thought it would be, so this is one of the reasons I went with EntityGraph, why I designed it the way it is. So now we get to, so we've created the database, we've transacted data. Now we're going to read some data. And this first bullet is just for anyone who's completely unfamiliar with pull. This is how Datomic documentation describes it. It's a declarative way to make hierarchical and possibly nested selections of information about entities. We'll see what that looks like in case you're not familiar, just to get a sense. But as far as features, it supports many of the features that you are familiar with if you know Datomic: wildcarding, nesting, combining wildcard and map specs, joins, forward-backward attribute navigations, and recursive pulls that are cycle safe. And this is just what it looks like. Again, we don't have to go through it in detail. This is just to get a sense. So in the first example, we pull the last name from entity ID1, and we get this map with just the last name in it. Second example is a wildcard, and so we get the whole entity. And the last example, we have a join there on person best friend, because we see in the spec it's a map, so that indicates a join. And then we get sort of more complex result there. And we can go on and do nested joins. And down below there, you see an underscore friend, and that indicates backward at reference navigation. And so we can do that as well. And there's more, again, This is just to give you a sense of what these queries look like. So now I want to just talk a little bit about the schema. And I want to focus in particular just on the parts that I didn't cover so much yet. So value type, we've already said, reference values only. Otherwise, you don't have to specify a value type. Is component. So component entities are just these entities that are meant as components of the parent entities. And the thing about them is they get removed if you remove the parent. You'll, like with the retract entity, it'll retract its components too. And when you pull, even if you don't join, if you pull that attribute, if you want that attribute, it'll pull the whole entity. So that's all. It's just a little convenience. DB cardinality. So if you want a cardinality many attribute, you have to specify it. You have to let me know. You have to let EntityGraph know. And the reason for that is because we need to know how to interpret a set in the EAV index. Because we can have any value, right, in the EAV index, including collections, including sets. So if we just see a set, we can't assume that this set represents, multiple values. Maybe it's a cardinality one attribute, and it just has the one value of type set. And similarly for AV indexing, we need to know, like, do we just index the one attribute, or is this supposed to be many attributes in the set, the outermost set, of course. DB unique. This is for declaring unique identities and values. Otherwise, you don't have to declare it. DB sort, this is novelty, you could say. So for in the EAV index, if you have a cardinality many attribute, there are many values there. And if we just store them in a set, that set is, of course, unordered, unsorted. And then frequently with user interfaces, we sort things, right? We want to display things in some kind of an order. And so you can actually specify DB sort on an attribute, and it'll sort it for you in the EAV index. So it'll use a sorted set, like a sorted Clojure set, or it can use the AVL set from Clojure Data AVL, which I'll touch on in a second. But basically, this amortizes your sorting costs. So you don't need to repeatedly sort the same data. Sometimes you might not do this. Sometimes you might resort anyway. It just depends on the situation. But when you need it, it's kind of nice to have. So I mentioned Clojure Data AVL. And what that is, it basically uses this data structure called persistent AVL trees as the underlying data structure for sorted maps and sets that, in addition to supporting everything like your basic Clojure core sorted collections support, it has these additional log time operations. So you can do things like rank queries. So give me like the third, or the fifth or whatever, or you can specify a key and it'll give you back the rank of that key. You can do nearest key lookups, right? So you give it a key and you get back the nearest key to that key. Maybe it is the same key, maybe it's something else, if that exact key is not in there. You can do splits by index or by key. So sometimes this comes in handy, and EntityGraph uses it in two ways. Or one way I already mentioned is for sorting cardinality many attributes within an entity. But also in your AVE index, we'll touch on that in a second, we can use an AVL map as well. So this is how we declare that we want an attribute to be in the AVE index with DB index. And as mentioned, unique and reference attributes automatically go in there. But then you can also specify what you want to go in there. And you can specify which kind of a map you want this index for that attribute to be. You can just have a regular Clojure map, and that's good if you only need specific values, right? So you can't do ranges, you just want that specific. Well, you can do ranges, but you're scanning the whole thing, right? So it defeats the purpose. So, but if you want just to get some value quickly, you don't need to pay for a sorted set. You can just use a regular Clojure map. Now, more typically, we want some kind of ranges, right? So we want the thing sorted, and you can use Clojure sorted map for that, as well as Clojure Data AVL sorted map, if you want those additional operations that I just mentioned. And both types of sorted map also support custom comparators, so you can choose your own comparator again if you need to. And so this brings us to reading directly from index. So as mentioned, when pull is not enough for our needs, we don't have data log or any kind of declarative query language, because we're hoping to just hand code it because it's going to be not common, and we're hoping to squeeze more performance out of it and a smaller footprint. And so in order to do this, we kind of need to understand the data model in the indices. And so we need to understand what our attributes, certain things about our attributes, like cardinality and uniqueness. And for that, I've provided you with some helper functions. Check adder, it just returns, you give an attribute and which property you want, and it'll give you like, this is cardinality many, cardinality 1. And then schema predicate functions, they basically give you the same information, but in predicate form, right? Is it a ref type? Yes, no, true, false. It's possible to build a query engine on top of these indices, but I question whether it's needed, or maybe some kind of I started on something like this, like some additional helper functions for common use cases, but again, hasn't been important enough to really pursue to the end. And this is just the two forms that the EAV index can take. I've already touched on this. The key here is how to interpret set values, right? Is this cardinality 1, so it's just one value of type set, or does this set, the outermost set, does it represent multiple values? And for the AV index, there's also two forms, but this is a decision I'm reconsidering. So let me explain. So on top there, we have sort of the standard AV index, what that looks like. And we have an example, right? So we have a person last name indexed, and you see for each value, there's a set of entities that contain that value for that attribute. But on the bottom now, if that attribute is unique, there's only one logical possibility. It cannot be a set of, well, it could be a set of 1, right? But rather than allocating a set and wrapping it in a set, I thought, well, why don't I just put the entity ID there and just be done with it? That seemed to make sense. But the reason I'm reconsidering this is because if you switch your attribute from unique to non-unique, or the other way around, then any queries that rely on that will also have to change. And that can be, I guess, uncomfortable, annoying. So maybe the trade-off is worth it. Maybe I do allocate a set and just, that way it's just easier you don't have to worry about the queries. Performance. So obviously for SPAs, performance is important. We don't want to skip frames, God forbid, but sometimes we do anyway, and it's okay in my opinion. Of course, depends on the specific thing you're working on, but it's pretty fast. I think it's fast enough just for general application development. And one thing I was pulled towards but have avoided is I didn't want to over-optimize for performance. Like, you could structure things differently. You can have like a different data model, maybe not have some of the features and squeeze every last bit of performance out of it. But that's not a trade-off. That's not a direction I wanted to explore with this approach, with EntityGraph. So I did not. And I did some benchmarks against DataScript and Asami, not like for any reason other than just to provide me with a sanity check that it's okay, it's pretty fast. Asami, by the way, is another library that kind of is in the similar space, EAV, triple store, but it's more of a database than like an in-memory thing, although I think there's an in-memory, there's an in-memory component to it as well, like you can have data in memory. Of course, performance benchmarks are tricky, and if you want to review, the details are all on GitHub, like exactly which benchmarks I did. But it's generally faster with some exceptions, and it does leverage Clojure's transients when updating the indices with transact, so that speeds things up nicely. So the status is alpha, and this will explain why. So just overall, the feature set I think is complete, or maybe there's some enhancements possible, but not planned at the moment. But with this feature set, I think you can sort of do everything you want to do. The intention is, of course, to avoid breaking changes by moving to new names. It's reasonably well tested. There's decent test coverage, but you can only be so confident in your tests. There's always a way to test more. And it's seen minimal production use, so obviously this is brand new. This is caveats applied. The error messages, I should say, are rather helpful, and I try to make it that way. So whenever I have an issue, there's some error. The error typically just explains to me what the problem is, and I fix it. Of course, it's easy for me to say because I wrote it, but I did try to make the error messages helpful. And highlighted in red here are the decisions that are still under review. So the first bullet point I already mentioned. The other two, so when you do pull and you pull a reference attribute, the value for that attribute will get wrapped in this map. DB ID and X is meant to represent the entity ID, just like Datomic does. And with Datomic, a map indicates a new entity, right? So you kind of visually see that nesting. With EntityGraph, it does not really, because you can have a map value not be a separate entity, right? But aside from that, with the UIs, with web applications like on the client, as soon as you do this, if you're just pulling the reference value and you wrap it in the DB ID, you got to stick that ID somewhere in your HTML, so you just unwrap it right back. So I think I'm going to just not do that, not wrap it, and just return like the raw entity ID as the value, not wrap it in this map. And then the last bullet point here, reversed references for unique attributes. Currently, they return a single entity because that's the only logical possibility, rather than a sequence. So let me just zoom in a little bit. If you have like a reference and you're navigating it in reverse, so you're seeing, okay, who points to me to this entity here from this attribute? If this attribute, even if it's cardinality 1, right, there can be multiple entities that point here from that attribute. But if it's cardinality 1 and unique, well, then there can logically only be one entity. So it doesn't need to be a sequence, right? It can just be that ID. However, we kind of have the same problem. If it goes from being unique to non-unique or the other way, the underlying query, like in this case, pull query, kind of breaks. And that's annoying. So maybe I'll change that. I think it probably makes sense to not do that. It's well documented. There's a REPL-based hands-on tutorial that you can just copy paste into the REPL and quickly get a sense. And there's like a running explanations. There's also documentation that describes the concepts and features. So what I've talked about today, but in more detail. It's on GitHub. There's the link, and I even have like a little document where it's a little raw, but I kept notes on like the technical decisions, some of them that I made, and what the reasoning was. So thank you very much. This was introducing EntityGraph. I'm Geo Grigoryan. That is my email. Again, free to contact me if you want to chat about anything really. And I guess I'll take questions now if there are any questions. Thank you very much.